Okay, so let us try this example. So given an elephant butt dam using mu or coefficient of friction of 0.75, assume gamma of the dam to be equal to 21.54 kilonewton per cubic meter. So here we are tasked to determine the factor of safety against sliding and the factor of safety against overturning, and then the point where the resultant intersects the base, then the maximum and minimum pressure developed on the foundation. So the assumption here is the uplift is varying linearly from full hydrostatic pressure to full hydrostatic pressure at the toe. So full hydrostatic pressure at the heel and full hydrostatic pressure at the toe, but the assumptions further states that it only acts 2/3 of the area of the base. So when we compute the pressure, take note the multiplier factor here is 2/3 because the effect of the pressure is assumed to be 2/3 of the area of the base. So first things first, we need to divide our dam with a corresponding composite area, y, to compute the volume. In here, the assumption is we're going to get 1 meter strip out of this dam. So we have subdivided the dam into 4 composite areas. And then we are going to determine base dimension of the dam. Anyway, vertical dimensions are already known out of the reference elevation from the illustration. Further, slope of each of the inclined portion of the dam is given. So by ratio and proportion, we can get the value of dimension A. We can say that A is to 1 is equal to the total length of this one is 85.4 and the corresponding slope of that one is 16. So by cross multiplication, we can get the value of A equal to 5.34 meters. Similarly, to get the value of the triangle adjacent to the slope 3:2, so we are going to get the dimension B using this triangle here and its corresponding slope. So the slope is in terms of horizontal and vertical components. So we can say that this base here is to 2, and then the height of this one is the difference between the elevation 85.4 to that of 24.4. So we subtract that to get this dimension, ratio it to the vertical slope, which is 3. So again, by cross multiplication, we can get 40.67. And then finally, for our base dimension C, again, we are going to utilize or consume the slope. Anyway, this is just 1:1. So therefore, if this is 24.4, therefore, C here will be also equal to 24.4. So they have equal vertical and horizontal slope. So next. So here we are going to project the 1 meter strip out of this dam. Okay, and then as usual, we have the center of gravity, then the center of pressure, wherein we are going to label this as PH1. This is towards the dam. Okay, and the distance of this hydrostatic pressure is 1/3 of whatever the height is. So the height is 82.3 divided by 3, that is 27.43. So on the notes that this has a triangular pressure towards the dam. Okay. Likewise, for the other side, there is also a horizontal hydrostatic force due to this liquid surface with a head of 24.4 meters. So the distance of that one is 1/3 of that head, 24.4 all over 3, that is 8.13 meters. And then from that, recall that weight is equal to gamma h. Okay, this should be gamma volume, should say. Okay. And then we're going to label all the composite area with its corresponding weight. Say for this triangle section, we have 1/3 of this dimension from here. Located is the center of gravity, so let us label that as W1. And then W2 is just a rectangle wherein we're going to get the mid dimension to locate the center of gravity. And then for this triangle also, we have 1/3 from the height of this. We have W3. And of course, the weight of water that will be carried and transmitted to the base of this dam. So of course, we wanted to label that as W4. And of course, we are concerned with this distance for volume calculation and the moment arm calculation later on. So we can compute that height by ratio and proportion of this triangle to the slope of this diagonal. So how is that? So horizontal D is to the horizontal 1, vertical dimension 82.3 is to vertical slope. So here's the ratio. So and then from that we can compute it by cross multiplication. So next is the weight on the downstream portion of dam, weight of water, okay, wherein the W6 is concentrated in. Of course, we are very much aware with the dimension of that one. And finally, this triangle for the dam, okay, W7. So our next task is to determine or compute all of the weight accordingly. So we will use this formula that W is equal to gamma H. Sorry, this should be gamma volume. Hence, W1 has a gamma of 21.54 here, 21.54 kilonewton per cubic meter. And then we are dealing with the triangle here. So we have 1/2. The base is B. Base is B, 40.67. And the height of W1 is the difference between 85.4 and 24.4, that is equal to 61. Okay, so this is the area times 1 meter strip to make it a volume. So therefore, W1 will be equal to 26,719 Newton. Okay. So next, we are going to get the corresponding distance of this W1 to the toe. We have here the toe, and this will be our reference line for that one. And here, W1 has its corresponding X1. Next, we have W2 is equal to gamma of 21.54. We have a rectangular shape here, B 40.67 by 24.4. So this is the 24.4 for the value of C actually. So we multiply it by 1 and get the value of W2 equal to 21,375.88 kilonewtons. Okay, next we have W3 is the triangle. The gamma is 21.54 times 1/2, base is 5.34, height is 85.4, and then multiply it by 1. So here we have 4,911.51 kilonewton. So by the way, all the units shall be in kilonewtons. Okay. Next, for W4, we have gamma of 9.81 times 1/2 times the base D, 5.14 meters, and then 82.3 times 1. So here we have 2,074.92 kilonewtons. So moving on to W5, I think we have skipped W5, so we have W6. So W6 is the weight of this water. Of course, W6 is 9.81 times 1/2 times 24.4 times 24.4 times 1 to make it volume. So it will yield to 2,920.24 kilonewton. Then finally, for W7, we have the unit weight of 21.54 times 1/2, 24.4 times 24.4 multiplied by 1 to make it volume. We have 6,412.03 kilonewton. So here we also wanted to compute pH1, gamma H bar A of 1. We have 9.81. So H bar is half of this height, and the height is 82.3. Then we divide that by 2, that is 41.15, by the area. The area is 82.3 by 1. Hence, we can get this value, 33,222.99 kilonewton. So similarly, for pH2, we have gamma H bar area of 2. We have 9.81 as the gamma. H bar is half of 24.4, that is 12.2, times the area of this is 1 meter, strip 1 by 24.4. And then we have 2,920.24 kilonewton. It's the value for pH 2. Okay. So next is the uplift forces that will be developed on the base. First, we'll have a pressure here more than the pressure at this downstream side because the head is greater than to the downstream. The head of the upstream is greater than that of the downstream. Of course, we will be having a trapezoidal orientation of our base pressure. So in here we have a pressure of gamma times H1, and that is 9.81 by 82.3. So we will have a pressure of 807.36 kilopascal. And then for this side, we have gamma H2, which is 9.81 by 24.4. And that will be equal to 239.36 kilopascals. And then from this, we can now compute for the uplift forces, wherein we just have to divide this into composite area since we have trapezoid. So this is a rectangular portion with the center of gravity at the mid. Say we label this as uplift 1 and this as uplift 2. So we'll just have to multiply the base dimension and the height, which is gamma H2. So we have the base to be A plus B plus C times gamma H2. So the sum of A plus B plus C is 70.41 times 239.36. So here, according to the problem, again, that the uplift force acts over 2/3 of the area of the base. So therefore, we should multiply here 2/3 for that condition. And that will be equal to 11,235.55 kilonewtons. We also compute for U2. This is actually in triangular shape. So 1/2 of the base, which is A, plus B, plus C, times the difference between this gamma H1 minus gamma H2. And the difference is actually this height of that triangle. So U2 is equal to 1/2 70.41 times the difference is 568. 807.36 less 239.36 is 568. And once again, we are going to multiply 2/3. And U2 is equal to 13,330.96 kilonewton. So the next step here is to locate all of these forces from the toe so that we can determine the righting moment and overturning moments. So starting with W1, say we have a corresponding X1 to that. So where's W1? Here's W1. So W1 is actually this total dimension minus 1/3 of B. So 1/3 of the base of this triangle, and that is B. So here B plus C, the dimension B plus C is 65.07 and B is 40.67. Therefore, X1 is 51.5 meters from the 2. So for X2, where's W2? W2 is half of B 1/2 40.67 plus C. So, and C is equal to 24.4. So, therefore, x2 is equal to 44.7 meters from the 2, or 44.74. Okay, so for x3, we have this triangle. Of course, we can utilize the sum of A plus B plus C, and then we'll just have to deduct 2/3 of A. So, 1/3 yan, 2/3 yung nasa kabila. So, therefore, we have to deduct 2/3 of A. x3 will be equal to 66.85 meters. So, moving on for x4. So, 4 is actually the weight of the water being carried and transmitted to the base of this dam. So, in here, we can also add all of this, A plus B plus C, the total, and then we deduct 1/3 of D. So this is 1/3 of the base, which is D. Okay. So we have 68.7 meters. And then for x6, so the weight of 6 is the weight of water from downstream side. Again, we have a triangle, so we'll just have to get 1/3 of C. Okay, so that is locate the centroid from the 2. Therefore, that will be equal to 8.13 meters. So for W7 or X7, we have this portion. This is actually part of the dam. So that is actually 2/3 of C. Hence, we can get 16.27 meters from the 2. Okay. So, actually, we have already computed for the hydrostatic forces distance from the 2. We have this one, 27.43 and 8.13. So, the distances of this U1 still yet to be determined. So, for U1, so XU1 up to the 2 is actually half of the sum of our base. We have 70.41 all over 2. So therefore, XU1 will be yielding to 35.21 meters. So likewise for XU2, so we've got here a triangular shape, pressure. So therefore, this dimension is 1/3. So the other one here up to the 2 is 2/3 of the base. So this is 2/3 of the base, A plus B plus C. That is 70.41 meters. So therefore, XU2 will be equal to 46.94 meters. Okay. So at this moment, we are going to compute for the writing moment. So what is our basis? Of course, we focus ourselves into the 2. Okay, this is the 2. Of course, from this 2, this is the pivotal joint. Of course, the overturning moment will be on this direction. Okay, while your writing moment will be on this direction. So this is writing moment tends to contradict, tends to contradict the overturning moment. So what are the forces along the RM direction? So from that, what are those forces? Say this is the writing moment. So writing moment. So what are those forces that will contradict or goes along this direction? Of course, we have W6 times X6 plus W7 times X7, okay, and then W2 times X2 plus W1 times X1 plus W3 times X3 plus W4 times X4. Okay. What else? So PH2 will go along the direction of the writing moment also. So that is plus PH2 times the computed Z2, that is 8.13. Okay. What else? So no more. So all of this weight will go along a counterclockwise rotation along the direction of RM together with PH2. Okay. So if we're going to substitute and compute for RM, we can get the value of 2,955,346.34 kilonewton meter. Now for our overturning moment, so all of the forces which will cause an overturning or a couple that is along the direction of the overturning moment. Of course, number one is U1 times XU1, the corresponding distance from the two, plus U2 times XU2. Then finally, we got PH1 times Z1 for this dimension. So if we're going to compute that one, we have overturning moment is equal to 1,932,665.6 kilonewton meter. So next is to determine RH, wherein RH is just equal to the summation forces along the horizontal. So basically, RH, we only have PH1 less PH2. So therefore, RH here will be equal to 30,302.75 kilonewton. So likewise for RV is simply equal to summation forces along the vertical. And those forces RV is equal to summation of the weights minus summation of the two uplift forces. So if we are going to compute that one with our derived weights and uplift, we will get 39,847.15 kilonewton. Okay. So next is to compute the first unknown. Okay, with this, we can now compute the factor of safety against sliding, and that is mu RV all over RH. Our mu given here is 0.75 times your RV, 39,847.15 all over your RH, we have 30,302.75 kilonewtons. So therefore, the factor of safety against sliding will yield to 0.99. Say this is 1.0. Okay, number 2. The second unknown is factor of safety against overturning. This is simply equal to Rm all over overturning moment. So our Rm is computed to be 2,955,346.34 all over 1,932,665.6. So therefore, factor of safety against overturning will yield to the value equal to 1.53. So there, take note, class, that factor of safety is unitless because it is noticed that units will just be cancelled. Okay, next. Number 3. The location of RV to the toe. So this is actually our X bar. So X bar is equal to Rm minus OM all over RV. Now, substituting the values, we can get a value for X bar equal to 25.7. And if we are going to investigate 25.7 from here, okay, so C, the value of C here is what? So the value of C a while ago was 24.4. So therefore, it is exceeding this portion, right? So therefore, our resultant will lie within the middle thirds. So this is RV. So remember that this is 70.41. So 70.41 divided by 3. So each of these thirds here, we divide that into 3 equal segments. This is 23.47 meters, 23.47, and this is 23.47. Hence, therefore, RV is beyond 23.47 from the toe. The computed value is 25.7 actually. So therefore, it is within the middle thirds. So 25.7 meter from the toe is within the middle thirds. So what is the meaning of that? Therefore, we had a good design on this case. Okay, next. Number 4. So, what will be the pressure distribution, okay, at the base? So, we are having a minimum and maximum value. So, we have derived this previously to be equal to RV all over B times 1 plus minus 6E all over B. Okay, so here E will be this dimension, okay, so this dimension, okay, so this is the center. From the center to this location of RV, what is the difference? So the center, so the calculation of E now will be equal to the total 70.41 all over 2. We deduct 25.7 meters. So therefore, E will be equal to 9.51 meters. So with this value, we can now compute for the maximum base pressure. So the base pressure maximum is equal to, our RV is 39,847.15 divided by the base, the sum of ABC. Okay, this is multiplied by 1 plus 6 times 9.51 all over 70.41. So therefore, the maximum base pressure is equal to 1024.56 kilopascal. Likewise, for our minimum, say we have a minimum base pressure, we'll just have to modify this one, and then the operation here will become minus, and then this is base pressure minimum. So with that, can be calculated be equal to 107.53 kPa. So this will be the answers. As a summary, the factor of safety for sliding will have 1. Factor of safety against overturning, we have 1.53. The location of RV from the 2 is 25.7, and that is within the middle thirds. And then the maximum base pressure is 1024.56 kPa. Finally, the minimum base pressure is 107.53 kilopascal. So this, it has a complete set of solution for analysis of dams. So this, thank you for listening and have a good day.